FTK imager does a very nice job recovering deleted partition, but if somebody challenges you, for example, can you prove that this partition has been properly recovered by your forensic tools? And in other words, can you explain how your tools recover deleted partition? Can you demonstrate your own knowledge regarding this information that you're trying to present as being properly recovered? So let's do exactly this. Let's prove everything and explain how the deleted partition is recovered on this drive. So when we click on unpartitioned space, that shows basic disk here, in this FTK imager tree, it shows us the MBR, which is the first sector on the drive, and its size, of course, is 512 bytes, and MBR stands for master boot record. And right here in our file data structures, we have information about the MBR. And its first 446 bytes contain boot code, and then the last 2 bytes contain right here at the very end of the MBR, and let me show you here in the detail panel, right here. This is our entire sector. Right here at the very tail of this 512 byte sector, we have what is called the signature value. The signature value looks like 55 AA, and those are the hexadecimal codes. And overall here in the actual file view inside FTK Imager and many other tools, we have this what we call a hexadecimal display or hexadecimal dump. So in this small column right here, it's trying its best to display the readable text, whereas on the left hand side here it shows us decimal values of every byte. So just a quick reminder that here I think in this handout I have hexadecimal notation, and it's just a little guide through what this hexadecimal notation means. So right here, if we look at byte right here that shows BF, for instance, this means that the first hexadecimal digit, the left one, corresponds of course to letter B in this table right here, and it simply means that the first or the left side of this byte contains a binary combination 1011, and the second hexadecimal digit here is digit F. So right here, of course, it corresponds to 1111. So that's the entire byte that basically contains the, so now hexadecimal values like this displayed help us to shorten the actual binary patterns stored in individual bytes of the surface of this disk. So basically what we do is we put it together like this. So this is the left side and this is the right side, and all together it becomes 1 0 1 1 1 1 1 1. So this in this notation, which is the hexadecimal notation, simply is a short version of specifying 1 0 1 1 1 1 1 1, which is much longer notation using binary notation. And so is every byte. And of course, this signature that we just talked about at the end of our master boot record sector, so here 55 of course corresponds to the byte that looks like this, right? So this is hexadecimal digit 5, and so it contains 0101 and the second one, which is also 0101, and AA, of course, corresponds to the something that looks like 1010 twice, right? So we have two of these, because 1 byte contains 8 bits, but 1 hexadecimal digit corresponds to 4 bits of information. So this is just a quick clarification what all this is shown to us. And also, of course, when we go to actually readable text, like over here, so for example here it says error, so this E right here essentially is encoded right here as hexadecimal 45. So I think also in this handout I do have this short table that gives us a translation of hexadecimal ASCII codes to the actual letters. So of course this once again, this hexadecimal 45, if you locate it in this table, so this is 45 right here, so it's printable encoding of printable ASCII character uppercase E, just like we have, of course, right here. So just keep this in mind, and this is how you would work with this information. And essentially it's all meaningful only at the level of individual bytes, because we're pretty much trying to display in this view only individual bytes.